All right, welcome to I think my eighth or ninth I think it's the eighth webinar. Today I'll discuss how to calculate the equivalent circuit for an ultrasonic transducer from impedance. So many of us who use impedance analyzers as seen here know that there's like a little switch and a little button that you can navigate to press, and it calculates the equivalent circuit, and you'll get these parameters and it'll fit a line through it. That's not what we're going to do. We're not going to press a button and have it happen. We're actually going to do the calculations. This is both useful when you're not doing impedance measurements on an impedance analyzer, you have a different product or a different custom system, or you just like to know what these parameters mean, how to calculate them instead of just kind of relying on your impedance analyzer. So first I'll discuss a couple of things that we'll go through today is basically what is equivalent circuit, why do we need to use it, and how to calculate it, how to compute that equivalent circuit. And I'll just mention my company. My name is Hussein Shakani, and I am the founder and lead consultant of my company, Ultrasonic Advisors, where I provide consulting services for companies developing ultrasonic transducers. I provide a lot of companies simulation services, but consulting on a whole range of topics in ultrasonic transducer development. So if you would like to inquire about working with me, give me an email, shoot me an email, sign up for a consulting call on my website, or just kind of respond to one of those emails on my email list. If you're on this webinar, you're going to be added to my email list, and you'll receive information for future webinars too. So with that, let's start and talk about the equivalent circuit. So what is the equivalent circuit? So we have our ultrasonic transducer, and if you're drawing ultrasonic transducer or a crystal oscillator, basically on a circuit diagram, it looks like this. But this diagram doesn't really tell you a lot about what is going on inside. So we use the equivalent circuit to better understand the specific dynamic and electrical components that create the effect of resonance and anti-resonance, of the off-resonance response. And so there's a common circuit. We're going to do the most simple ultrasonic circuit. And if you guys remember from last time, we talked about the capacitor model, like off resonance, let's say at 1 kilohertz for an ultrasonic transducer. We just, your piezo element is a capacitor, but I said, hold on, you can actually split that up into two, into two capacitors, one representing your mechanical branch or your mechanical energy. So you can call that the QCM. And, there's so many different terminologies floating around kind of in the ultrasonic transducer, like text and reports and everything. So I just kind of make up my own subscript sometimes as I go. So here we go, CM and CD. So this would be the dielectric component, and this is a mechanical component. And I mentioned last time, hey, if you bond a piezo ceramic to a plate, to like another substrate, you're constraining the mechanical component. So you'll actually see a reduce in the mechanical component, and you'll get an overall decrease in the capacitance. And that's the way we use equivalent circuits to understand, and we split apart these components. So the equivalent circuit that I'm going to be talking about today is the Van Dyke equivalent circuit. Let me just move my video. So that has also splitting of the mechanical and electrical branches. So we have an LCR circuit, so capacitor, inductor, and a resistor. And we have another capacitor here. And the equivalent circuit analysis is basically to use, and if you have these components, in this first slide, I had these components here, right? This is equivalent circuit. Everything's already calculated for you. But if you had actually simulated this exact circuit in a simulation program, you would get your resonance and anti-resonance. So that's kind of cool that you can use this circuit to get resonance and anti-resonance. And the reason we discuss the circuit is because a lot of these components all relate to physical, mechanical, and electrical components there. So this is the equivalent circuit. It has a mechanical branch and it has an electrical branch. This is not the only equivalent circuit there is. There's also an equivalent circuit for and this is the resonance. This equivalent circuit is based off the resonance frequency, but also encompasses anti-resonance. There's another type of circuit which can also focus on the anti-resonance, but also includes resonance, because to have this circuit work for a large frequency range, you need to have you need to encompass a lot of other features. So, for example, at off resonance, at low frequency, this circuit right here simply becomes two capacitors. So because basically at low frequency, inductor is just a straight wire, and if the resistance isn't that high, you basically have these two capacitors with very high impedance at low frequency, and that would then lead to your capacitive behavior at low frequency here. And then at the resonance frequency, we have this LCR circuit, which then resonates, creates a lot of current flow, so it dominates the impedance. And you guys probably already know this is impedance and frequency, so it dominates, so it creates this local minimum. Then what happens at anti-resonance is very kind of interesting. So after, and for an LCR circuit, basically, the response is like this. So so this is the capacitive region, this is the resonant region, this is just an LCR, and this is the inductive region. So at high frequency, the inductor is going to block more current, so it will dominate for an LCR circuit. So then in the inductor, I'll just call it L, or it's also called, I think, I. So basically what happens is there's this inductor who has one phase, and this capacitor then cancel the current. So what happens after the resonant frequency, this is drawing a little bit, just ask questions if you have it. I can repeat this if you want me to repeat this explanation. But after the resonant frequency, the current coming out of the mechanical branch is like this. And the current coming out of the electrical, this bottom pure electrical branch, which just represents the clamped capacitance of your transducer for that resonant mode, it's completely opposite. So that creates destructive interference between this mechanical branch and this electrical branch, and then therefore you have this high impedance because the two currents are canceling each other out. Now you still have movement and current, which represents power in this case, but that is kind of a little crash course as to, well, we have this, and as you keep going up in frequency, now your capacitance its impedance is lower than the LCR branch, therefore you return to a capacitor. So I'll just rehash that on another slide here. So we're talking about basically dynamics and equivalent circuit. So again, let's draw it. So you have your capacitive behavior. Basically, that's your dual capacitor. But when you measure it, you only measure one, obviously. And then here is your LCR circuit. That's the mechanical part. And then here, it's basically like this inductor and this parallel capacitor going at each other, and this is an electromechanical phenomenon. For most transducers, I'll say for most transducers, the anti-resonant frequency is not a mechanical resonance. It is a resonance due to it is an anti-resonance, which is minimal current, high impedance due to canceling of capacitance. Did you know? Question: did you know that if you have a transducer, and I'm just going to draw it as a crystal, and if you intentionally add another capacitor here, like, hey, let me just stick on a 5 nanofarad capacitor. If you measure this, you will actually get, and let me just put some color for you guys. All right. So let me just put this in blue. What's going to happen is your anti-resonance frequency will decrease. So you can simply add a capacitor in parallel and change your anti-resonant frequency. That kind of tells you, like, this isn't as mechanical as I thought it might be. This isn't a resonance like we're kind of taught in terms of mechanical resonance in the same way. So those are the dynamics. So as you would imagine, the mechanical branch represents the mechanical resonance. There's an LCR circuit, and these two components are going to create your resonance. You have your resistor, which is in this particular circuit, it's the only damping consideration. We're not considering dielectric losses like the phase angle at low frequency. That isn't as relevant at resonance. And you have your parallel capacitance here. Or what I'll say is your clamped capacitance or your pure dielectric capacitance. There's a lot more to say. This is obviously a simplistic model of a complex device. So it is missing some things, but it tells like 95% of the story, and it's extremely useful for understanding. And if you wanted to, you could add multiple modes, like multiple LCR branches to represent many modes. But in particular, we're just considering one mode of operation in most ultrasonic transducers, especially power transducers. So it's not really important or valuable to add extra branches. There's a question, and the question is, does the two capacitors in the added capacitor circuit overpower the inductor? How does it shift the impedance versus frequency? So basically the frequency at which this inductor and this capacitance equal in terms of output, like if you had the frequency. So as the frequency increases, the inductance is causing lower and lower current, and the capacitor is causing more and more. So there's a point where they meet, and that is the optimal cancellation point. So once you get past that cancellation point, the capacitor is going to dominate again because it's a higher, it's a lower impedance. But until that point, at the exact point that they meet in terms of how much current they're producing, then they have maximum deconstruction, highest impedance. So does the capacitor overpower the inductor? It's not really overpowering, it's just shifting to where the resonant point is. It's just simply not resonating at the same point anymore when you add that. So if this value increases, like then the capacitance will start to increase faster. The current will be more in this case. So it's basically like adding on the capacitor here. So it'll be the resonant anti-resonant frequency will shift lower, because this capacitive current will grow faster than originally by itself. So how does it? That's kind of how it shifts. How does it shift the impedance? I think the impedance will decrease. If I'm not mistaken, the impedance will be lower. It won't be as high, if I remember correctly. Yeah, it goes up to a lower frequency because it matches the inductor. And this little capacitor, that's true. This little capacitor doesn't have, it's still saying something. This little capacitor in that region is practically kind of reducing the inductance. I'm not kind of getting into semantics, but yeah, there's that little capacitor in the LCR part is still active, but it's not really playing a dominating role. It basically reduces the practical inductance. So that's that, I guess. The next part. All right, so that's the equivalent circuit. Now I'm going to explain how to calculate it, but why do we ever would want to calculate that? Like, it's very good just to list things like resonance frequency and resonance impedance and the coupling factor that we usually do, and you just go with the measured off resonance capacitance. And why not just stick with these values for characterizing transducers? Why even bother with equivalent circuits? So one, from a teaching perspective, it's good for getting a deep understanding of your transducer. A lot of times, unfortunately, we treat our transducers as a black box. We don't really understand it. We just assume that we're purchasing some crystal. We should be able to attach it to a substrate and it should work in some way. And if it doesn't work, then something is like weird, and people get panic and get nervous when they don't understand their devices. So just on a confidence level, to be confident in the technology that you're using, this is definitely going to help. The other thing is in circuit modeling. So if you have, a circuit program where you're designing a driving circuit, to drive your transducer, you can actually represent it properly in, like, for example, in a program like LT-Spice or whatever other circuit simulation program you have, if you actually have a discrete representation of that circuit. If you have this, you could go plug it in, and then you can test how your drive circuit is going to react, because it's, you know, your drive circuit doesn't put out a perfect 50 volts because it has an output impedance. It has other effects. So that's the first case. So the other thing that happens when you use the equivalent circuit is you're better able to describe your transducer. So yes, you have resonant frequency, but within resonant frequency, there are a couple of things put in, like there's the L component and the C component, and I believe the inductor indicates more toward the mass of the system, and the capacitance is more akin to the stiffness of the system. So if you have a situation where you have let's say you have you have one transducer. You have one transducer. Let's give an experimental example. Now, you don't always want to, like, this is a tool in the toolbox. It's not the tool only. So there's one transducer, and you have, you know, two fixtures, right? This is very common. Like, hey, you have in fact, and you want to understand, like, you want to characterize, and you're getting different results. So you have a different resonant frequency for the first one. You have the different resonant frequency for the second fixture. But then you say, hey, let's do this analysis, and through the analysis, you found that, let's say, your inductance was different. So you figure that, hey, this is a maybe mass loading effect. So what might in these two fixtures cause that? Or you find a difference in your capacitance. So you feel like, okay, there's extra stiffness being added, or there's a difference in your in the resistor. So just changing the resistor changes the damping factor, or changes the quality factor, which can shift the results all in and of itself. So you're kind of more able to say what caused the differences, rather than just rely on more a mixture of properties like that would come from that would come from just a resonance behavior, or just measuring resonant frequency or resonant impedance. You can kind of dig in a little bit deeper if you need to. So the circuit components reflect real world origins of behavior a little bit better. That's one strong reason to use them, although I haven't seen companies use it extremely commonly, but it is still pretty useful to, if you're really digging into your analysis, which often does happen for ultrasonic transducers, and troubleshooting and doing experiments. And the more ways you can analyze your data, the better, because you're obviously not repeating the whole experiment, which is very costly. You're just analyzing it differently. So you may find a way to explain this better. It may be easier to explain to your colleagues. Once you show a circuit diagram, it's easier to explain to your electrical, for example, engineering colleagues. So that could be, those are other benefits, kind of softer benefits in terms of like explaining to others what's happening in your device. This is one which is the one that I think you guys might, I don't know, surprise is not the right word, but I think you'll be very intrigued by what I'm talking about, linearizing the results. So all of this analysis, this equivalent circuit only works when you have a linear system. These are all linear components. There's nothing nonlinear happening here. It's just based off the linear piezoelectric effect, or an effective piezoelectric effect for your transducer, and there's a resonant frequency, and all of that is good in linear components added to each other. Nothing in this ultrasonic behavior, resonance and anti-resonance, it's not something beyond normal mathematics, basically, of circuits. So what do I mean by linearizing? So what happens if you have a frequency sweep, and you have your resonant frequency here, and let's say you have your displacement, I'm going to write D for displacement. You know that at the resonant frequency, it's maximum. And for a linear system, eventually at a really high frequency, it becomes about 0. And there's a region here, it's about constant, low frequency. But the thing is that the properties depend on the displacement level. So if we're talking about the resonant frequency, or even the Q factor, so Q factor, the resonant frequency, or even if you want to take things like this capacitor here, like C1, let's say, this is going to be called C1 soon. These are all functions of displacement, or you could say velocity, depending on how you want to represent this. So they're inherently nonlinear values. So yeah, small signal. Yeah, kind of. Yeah, small signal is kind of like linear, right? Somebody wrote in the comments. So man, I think I'm talking a lot here. I'll go through the calculations a little more fast, more quickly. So I do also have an Excel sheet that you can take a look at later as well to do these calculations. But these are inherently nonlinear. So basically, at anti-resonance, you don't have much displacement. At resonance, you have a lot of displacement for a set voltage. So you basically have a different quality factor and a different like system stiffness at resonance and anti-resonance. That's not going to play out very linearly. You're going to try to fit a model to it. It's not going to work. However, for your impedance analyzer, uses such a small voltage that it doesn't really matter. The displacement at anti-resonance and resonance are still about zero, even though the resonance is probably 100 times higher, 1,000 times higher. It's still about zero. Because of the low voltage. But once you have any significant amount of voltage, you also have your other parts of your system, your amplifier playing in. So what do we do in this case? Generally for amplifiers, they basically have an output impedance. So what this basically does, it's like a resistor. Like there's the voltage source here, and it effectively keeps the voltage constant at the resonant frequency. Not the voltage, sorry, the current constant, because the more this system draws in current, the voltage will automatically drop due to this resistor. So that really does happen for most drivers. So what kind of happens is that in reality, like we drive our transducer and we kind of end up with this flat spot. This is the actual driver with an actual transducer. This is what ends up happening. So this region is kind of constant displacement. So if you can calculate things like coupling factor, if we can calculate things like the theoretical anti-resonance frequency, what it should be, if we were to theoretically keep this displacement constant, what would be the anti-resonance frequency? And that also then further allows us to describe a transducer. So basically, we can use the equivalent circuit to really narrow in on a specific region where we have linear behavior and extrapolate more properties versus doing incorrect analysis from doing like 100 voltage sweep across a transducer and really not having comparing apples and oranges to calculate properties. It's not a good thing to do. Friends don't let friends. Do linear analysis on nonlinear systems unless they can find a small region where there's linearity. You can ask more questions on this later if you are doing high voltage frequency sweeps and you're trying to analyze impedance to get meaningful properties. Let me know and I can answer some more questions about that. Whew. All right. So how do you calculate that off resonance or that equivalent circuit? So like last time, we first start with measuring a lot of different properties. We measure our off resonance capacitance. We measure our resonant frequency according to the maximum resonance conductance. It's not always the same as the minimum impedance, and I kind of discussed that in different areas, and I have some plots soon, so I'll talk a little bit about it. We measure our resonance Q factor, our anti-resonance frequency, and our anti-resonance real impedance, I think this is called resistance. So this is a kind of basic order that I'll be doing the calculations. Let me just draw out a little diagram just to show you what components are called what. So we have the L, okay, C, R. The only thing creating losses is this resistance. So we just call this R1, C1, L1. If we have multiple branches, then we can go L2, C2, R2, but we're just doing one branch. That's the way I'm rolling today. And this is C0, which is basically I'm considering to be a pure dielectric case. There's nuances there, but it's just easiest to describe it like that. So let me talk about the measurements and then we'll get into calculations. And I'll try to make sure I finish in 15 minutes here. So like most of my videos, I use this oscilloscope, which is measuring current, which is delivering voltage, a sweep. It's measuring current using a ground side resistor. I'm doing the appropriate mathematics in order to calculate the actual current and the actual voltage dropped across the transducer, not the entire voltage. So keeping all that relevant, and I am using this transducer that I'm showing here, which is the ultrasonic cleaning transducer. So first we want to measure capacitance. Now you can use the capacitance meter like I mentioned last time, or you can use just, as you see here, I just sweep frequency from 9,000 to 11,000 hertz, and you can then calculate the resonance the resonance impedance, so at 10,000 hertz, we have 4160 ohms for the resistance. All right, and then we have, and we need to use radians, so this is a reminder. You convert that 10,000 hertz to radians, and you get obviously 62831 radians per second, and then 1 over, the impedance multiplied by omega, that equals the capacitance. And this ends up being 3.8 nanofarads. So what we've just done, we've calculated 3.8 nanofarads. So what does that exactly tell us? So this part right here, the top and bottom added together is 3.8 nanofarads. So basically C0 plus C1 equals CT, and that's 3.8 nanofarads. So we actually have calculated not a value just yet, but the addition of two values. So that's actually one equation that we have. All right, let's continue. So that we already getting some progress. This is probably the easiest step there, to calculate capacitance. Then the next one is the next one is impedance measurement. So this is the resonance response. Let me move this here. Okay. So this is familiar resonance, anti-resonance. The phase goes from -90 to +90 and back down again. If you had just an LCR circuit, this would go down and up and continue to fly up. It would just fly away all the way to infinity as an inductor continues to increase in impedance. And this phase would stay 90, like an inductor would. But because we have that parallel capacitor, it cancels the voltage and it overtakes the inductor, like somebody was saying. And then it just says, I'm in charge now. So another way to actually measure this value directly, C0, directly, is to use a frequency after the resonance frequency, after the impedance frequency, let's say somewhere out here, to measure that directly, because at that point the C1 is no longer producing an effect because it's blocked by that inductor. I'm not doing that today. There's a couple of ways to make this measurement, but so just as a okay, so let's see. And then, so here's the plot. So this is exact same data, except I'm plotting for blue. I'm plotting the real, I'm plotting conductance, which is the real admittance, and I'm plotting real impedance in red. So real impedance peaks at anti-resonance, and real admittance or conductance peaks at resonance. That is a better way to calculate the resonance and anti-resonance frequencies, and also a better way to calculate the Q factor, and also can directly allow us to calculate R1. So how do you calculate R1? So you take your resonance admittance, which are the losses occurring at anti-resonance, at resonance frequency, it relates to that, and you take the reciprocal. That is R1. And that, and I already have the notes already here. That ends up creating a resistance for this case of 14, about 15 ohms. Because that real admittance is 6.7 e to the minus 2 Siemens. So therefore we're able to get this looks like 15. Let's sort of do this. So yeah, about 15 ohms there. So we calculate the resonance frequency. Sorry, the R1. So now we have R1 checked. We have these two together. It isn't really completed, but we're starting here. So let me kind of go over the rest of it. And yeah, so next thing I do is I calculate the quality factor. So if you see here, so if you look at this plot, I zoom in around this area right here. I zoom in the frequency and I get this. And what I did here is I looked at, since this is the real, this is the conductance. So the maximum conductance is the resonant frequency. And then I go half the magnitude from that, left and right in frequency. So I have this cursor 1 and cursor 2. So if you see here, the resonance frequency is at 64 millisiemens, and therefore the half power bandwidth will be at frequencies of 32. Oh yeah, 32. So there's approximately 32, and the cursor values here, you can look at, I did 30 and 36. So I'm not, you can do interpolation, you can do higher frequency, more resolution. You have options there on what to do. Yeah, okay. You have options as to how to calculate the quality factor, how accurate you want to go. So as you might know, if you do the resonance frequency, divided by F2 minus F1, that's the bandwidth. Then you get a quality factor. In this case, I already have it I already calculate it. And the other time I did this, I'll have notes on the side. These are a little bit different data. It's just from a different day, and depending on how you hold your transducer, you might know that you get different results. So in my calculations, I used ones that's 497. This says 442, but my calculations went 497 in terms of the quality factor. All right. So there was a question: is admittance just 1 over Z? So there's a little bit of a nuance here. I would admit personally, I get a little bit confused going back between admittance and impedance. Let me just get to this one of these diagrams. I get a little bit confused going back between admittance and impedance. However, what you can understand is, let's see. So 1 over the imaginary impedance is not, for example, the real the imaginary admittance. It's not that. You have to do other kind of trigonometric excursions in order to get there. However, when you have the real admittance, in this specific case, because the losses are only occurring because of this, and in this specific case, then you can actually do this. You can actually take the reciprocal and you can get the resistance that occurs in the LCR branch, because yeah, real admittance is never going to be affected by an imaginary an imaginary contribution toward those values from a capacitor. So the minimum, it's kind of a way to weed out the minimum resistance. So now for high Q transducers, you can actually just use the resonance impedance as the resistance, but for low Q transducers, or in general, this is the best way to use the admittance for the real admittance for that, because the real admittance, because losses are only coming from the LCR branch, so this focuses right on that. If you include imaginary components, you're going to get a mixture of contributions. So let's see where we are so far. So we've done the resistance, we've done the capacitance, we've measured the Q. So the Q doesn't show up here yet. Like, where's the Q? It's not really a value. So let's go there. So let me just pull out some things. I have another diagram. 1 second, pull this in here. So here are some equations. So from this equation here, so if you ignore, right now, you can ignore this part here. What I mainly will do is I use Q to solve for the capacitance. So capacitance equals 1 over omega, which is the resonant frequency, R1 divided by Q. And this gives you C1. C1 equals 5.38. And I think I did, so sorry, you can also do capacitance first, however you want to do it. So it equals 5.38 nanofarads. And since we already know CT, right, I did the total capacitance, that's the off resonance. CT minus C1 equals C0. And I have a better spreadsheet for this. I'm just like, I'm writing this so it's like, I think it's more engaging. Yeah, Q means quality factor. Yep, you're right about that. So that's C0, and C0 ends up being, oh, sorry, this is not nanofarads. Sorry about that. Let me just delete this here. This is actually 0.538 nanofarads, and C0 equals what? 3.26 nanofarads. So it's much larger. So C0, C0 is equals like C1 times about 6, you could say. So it's 6 times larger. So this is necessary. So basically this says when you have this transducer, there's going to be, for an off resonance behavior, you might have 6 times more energy in the dielectric, stored in the dielectric energy versus the stored mechanical energy in terms of elastic energy. Oh, this seems interesting. Mechanical and electrical energy ratio. This is going to be really closely related to the coupling factor. So the coupling factor can also be defined from equivalent circuit analysis, which is kind of cool, I think. So the coupling factor, you can also, as you guys mostly know, you can measure that from resonance and anti-resonance, the coupling factor, but you can also do it from this equivalent circuit analysis where we have C mechanical, which is basically the converted energy, and C total. So this is the converted energy because you're inputting as electrical, and this is the, how do I say this? This is the this is the total. So this is also the coupling factor, and there's like some square root. Is there a square root in here? Yeah, there's technically a square root here. This is actually technically squared. I don't know if anyone on this call knows why it's people square it or don't square it. This is a traditional representation of coupling factor, that it comes squared. I don't know why they do it. If anyone does know, please feel free to put it in. That's something I've kind of been, I haven't thought a lot about it, but I've thought a good amount about it. I'm not sure why people just leave this as squared, why they insist on putting a square root here. I guess because when you're calculating it, you square these values, right? If you guys remember, you square those. So I guess, if they're square, they should put a square root on it. I don't know. It seems like that's what that was done, and maybe it was done at one point and it never changed from there. So you can calculate coupling factor from all this. So where are we at? So let's go back here. So now let me just get a different color just to show. Okay, we've done this. We've done this. We've done this. Now the only thing left is the inductance. And the inductance also held, obviously, LCR circuit. Okay, that's kind of, the resonance frequency is related to the L and C. Yeah, it's going to be quite a simple. I'm not got questions yet. Then we have this right here. So from this, let me get that. This equation, and you can, if you just solve for the L, I forget what it ends up being, but yeah, I may have said something somewhere. I don't remember everything I've always said. So yeah, I think I said something. I probably remember at sometimes I forget things, as you might notice if you watched enough of my lectures, but most of the time I remember enough to explain things. That's what counts, I guess. So this is obviously a function of the resonant frequency, this and C1 like that we already know. So this ends up being a quite large it ends up being I think it's going to be 29 millihenries. And I'm going to show you a spreadsheet in a second. So now we've actually calculated each component. There's actually a different and you know one thing you guys notice is that I didn't use anti-resonance at all for all these calculations. I calculated the entire thing without using anti-resonance frequency. So that kind of like, that's interesting. You do know from the coupling factor equations that you can calculate this coupling factor using resonance and anti-resonance. And if you did it this way, you would not use this square root symbol. If you just had it like, oops, there you go, equals there. You would not use a square root symbol. So you can calculate anti-resonance from this equation as well. And if you did that, an easier way to do it is 1 minus resonant frequency squared over anti-resonance frequency squared. That's easier representation than doing it this way. You can actually solve for this much more easily. Yeah, I'm going to be uploading this video, not today, probably Monday, or when I get around to it very early next week. So that was just answering something in the chat. So you can actually calculate the coupling factor, and from the coupling factor, you can get to you can also then calculate the C1. So there's actually two ways to do this. Let me just if you can actually just use the quality factor and the resonance frequency behavior to get all of the properties, or you can use the resonance frequency and anti-resonance frequency and ignore the quality factor, and you can also calculate all the properties. And there's a few more ways to do the equivalent circuit analysis. I'm going to show a spreadsheet right now, and then I'm going to finish with that. So this is my analysis. I measured resonance, resonant frequency, resonance frequency. We got somebody drawn on the screen from I didn't disable it, I guess. Sorry. Yeah, don't draw on the screen. Hands down, hands on the table. Don't draw on the screen. Somebody's doing that. But okay, so 39 kilohertz, and then we have the resonance admittance. You know, I find the half power bandwidth. I got the Q. Perfect. I measured the resonance and anti-resonance frequency. Oh, impedance. I didn't use that yet. I did all the calculations that I mentioned for R1, 1 over admittance, L1, C1, C0. Then I did this coupling factor analysis. Okay, and this is the coupling factor according to Q and resonant frequency. All right. This is the coupling, this is the coupling factor according to anti-resonance frequency, this traditional one where you have that squared, these square terms for resonance and anti-resonance. If I use this keff coupling factor definition for these, and this again, right, it's not squared, I use a square root here. So if I use the coupling factor definition, I can also calculate C1, and then I go backward the other way. Then I use the resonance frequency, equations, and I get L1 and C1. So if I calculate the equivalent circuit using resonance frequency and Q, this is what you would have to do if you have a nonlinear system. So this actually puts this system to the test. Is it linear or nonlinear? How bad is it nonlinear? Because these should exactly match, or maybe how messed up are our measurements, because this also can highlight whether our measurements are consistent with the linearity of the system that we believe exists. So I can calculate these two. So the capacitance is the same, the off-resonance capacitance. We don't change that. There's a slight difference in C1 and L1. R1's exactly the same because we measured that in the same way. In this case, for the anti-resonance frequency, this is the measured one. This would be the computed anti-resonance frequency based on the coupling factor. There's a comment in the chat. I'll just get to that right after I'm done with this. I'm done blabbering here. This is the quality factor that it comes from the anti-resonance, the resonant frequency, like the normal half bandwidth way. This is what the quality factor should be according to this equivalent circuit analysis. So this was calculated using equivalent circuits. This was calculated using direct measurements. So they're actually a little bit different. So they're about 50 different, which is not really, which is like within usually experimental variability, but they still are different. They're not the same. Now they're gonna look kind of like, so this is the three methods here. This is the blue in the experiment. This is the Q method, basically quality factor and resonant frequency, the method I went to in detail. And this is the anti-resonance frequency method, which obviously emphasizes we must get the anti-resonance frequency lined up. So that's how it all went down here. Now you may see that the Q method is not accurate. That is probably not true. The Q method is accurate. However, there are probably some nonlinearities occurring at anti-resonance because the difference in amplitude that causes these differences. So this actually may highlight the fact that even the small differences in the output between the difference between the displacement at resonance and anti-resonance is causing enough nonlinearity to cause an estimated frequency change of however many hertz this is. This is about what is it? It's about almost 200 hertz nominally. It's 200 or 150 hertz. So that difference is actually caused by nonlinearities. So yeah, you measure things on your impedance analyzer, but like don't think that's like it's like it's working perfectly. There are other issues existing here. So I would say it's more accurate to use the Q method if you're like really going for the accuracy part, because it'll calculate an appropriate coupling factor. So what's to lose if we just do it like this way? Well, you're not measuring the appropriate coupling factor anymore. You got this now, may not be a big deal in this case. Like you measure a coupling factor of 0.36, which is the anti-resonance method, which includes experimental errors due to differences in amplitudes between resonance and anti-resonance in terms of displacement. This doesn't. So it's important to understand it. Now, I don't want you guys to freak out and like feel like the world's ending. You never made a good measurement in your life before today. I would admit, for the most part, probably 99% of the cases, I don't really go into this difference. Because I think it'll be consistent. So most of the time you're looking for trends. So we're looking for trends that'll be okay. But if I really wanted to dig in and understand the system better, or I had a limited measurement setup where I don't have the ability to drive at a consistent velocity or consistent displacement at resonance and anti-resonance, I may utilize this to calculate a coupling factor that I can use to explain to people, because they're more used to seeing that instead of coming up with kind of a new measurement system and a new values. And so that's the case. So I'll answer this last question here, and I will then I will go forward and take any other questions off, not on the not recorded. This keeps copying this. Okay. All right, can't click here. Can I draw? I can draw. Sometimes this happens. So the question was asked, how do you calculate the total capacitance? That was the capacitance at 1 kilohertz or 10 kilohertz, as I did, off resonance. And then how did I get C1 and C0? I actually measured the Q factor. That's the first thing I did. And then the next thing I got R1 from from the real admittance at resonance. Then I use the definition of the resonant frequency. A resonant frequency equals 1 over, I think I just forget these equations. Probably the engineers of the past never forgot an equation in their life. It may not be one of those. Yeah, it's this one. So I use this equation then to calculate. No, it's not this one. Sorry. What am I doing? Then I use the quality factor equation to calculate the capacitance here. This is actually C1 and R1. So C1 is the only thing missing here. And then once you have C1, C0 equals CT minus C1. And I hopefully that explains it again. You can feel free to watch, and I'll also upload this document here. Now that you've gone through this with me, it'll probably be self-explanatory. There's also kind of a lot of calculations in order to calculate impedance from these values. It's a little bit redundant and unnecessary, but I don't know if there's a specific equation. So basically, I stepped through all the steps in order to actually calculate how to calculate the impedance, because these are actually calculated from the values. So it's kind of neat how to do all that. And with this, I thank you for joining, and I will stop the recording and ask for questions. Stop recording.